Robert Platt is a professor in the departments of Epidemiology, Biostatistics, and Occupational Health, and also in Pediatrics at McGill. He holds the Albert Boehringer Endowed Chair in Pharmacoepidemiology, and he's the principal investigator of the Canadian Network for Observational Drug Effects Studies, or CNODES. I think this group is primarily based in the Jewish General Hospital, if I'm not mistaken, at least in Montreal. His research focuses on improving methods for the study of medications using administrative data, with an emphasis on methods for causal inference and a substantive focus on medications in pregnancy. Robert holds the important position now of editor-in-chief at Statistics in Medicine, and he's also served on other editorial boards like American Journal of Epidemiology and Pharmacoepidemiology and Drug Safety. So thank you very much, Robert. And you'll have a catchy title. We're all waiting to hear what you have to say. Thank you.
Thanks, Nandini. Thanks for the invitation. And I look forward to talking today about machine learning in pharmacoepidemiology, or in epidemiology more broadly. I'll say this, that since my focus is mainly on pharmacoepidemiology and drug safety, my examples and questions will come from there, but the principles, I think, underlying what I'm talking about today will apply across observational epidemiology and clinical research more broadly. Okay, just some brief disclosures. And here's what I'm going to talk about today. I'm going to, probably you've seen a lot on machine learning before, but I'm going to try to set the stage just in terms of some definitions and some understanding from my perspective as a statistician epidemiologist who's learning about machine learning, so that we have our terms right, we have what we need to know right, and we can think a little bit. I'll look at some simple examples of how machine learning can be used in pharmacoepidemiology. Then I'll go on and talk about some of our work in my research group, where we're looking at methods to use machine learning in pharmacoepidemiology, and really with the focus on machine learning for confounding control. So that is, given an observational study, we know it's confounded. Can we use machine learning tools to do better than we might with sort of traditional statistical tools? And we'll focus a little bit on the high dimensional propensity score, which we can think of as very basic machine learning, and then some more sophisticated methods. And then I'll end with some discussion of targeted learning and other double robust methods, which is sort of the most cutting edge work I'll talk about today. I can't promise I'll get all the way to the end here. I think the talk is probably a little bit too long, but we will see where we get. Okay, so let's move to the first chunk of work I want to talk about. What is machine learning? So machine learning is a broad class of methods, and you'll see many, many definitions of machine learning. But the basic idea is you want to summarize data or predict from data. And the idea is the model learns from the data it's provided to identify patterns and to make or provide decision information. Ideally, or technically, machine learning is without human interference. So you set the program going, you let it go, it produces a result. And I think it's reasonable to argue that most statistical methods fit this definition. That is, logistic regression with a set of variables. If you don't do variable selection, logistic regression learns from the data it's provided to identify patterns and make decisions about the associations or predictions in the data set. The focus, however, in machine learning or in machine learning as it's used, as I understand it, is on automation of this method, of these methods. So the idea is to create automated methods that produce predictions or identify patterns or otherwise. I always think of a very simple, as a very simple benchmark for what I'm thinking of when we're saying this is things like credit card fraud detection. Credit card fraud detection methods are working with enormous amounts of data with probably millions, if not billions, of transactions every minute, and they're building learning models that predict this whether a transaction is fraudulent or not. So the idea there is you've got this enormous data set, you've got this algorithm that may be changing itself on the fly to give the best prediction of whether a particular transaction is fraudulent or not. Another way to formalize a little bit more what we're talking about is an algorithm that learns from data or predict outputs from data. And in our case, we're mostly going to be talking about things like disease status from inputs, covariates, in a new sample, having first been trained on a training data set. So start with a data set, past history, past credit card transactions. You build the model, you predict on a new data set of credit card transactions, and then you predict, and then if things are working, you implement that model in practice, and it goes off to predict fraud in practice. The key then is that you may go back from the test data to training data, adjust the model, and come back again. This may be a recursive process, this learning process. So one of the challenges I really had with this work and this literature is just the language that we speak, and as is often the case with methods, when methods come up through multiple fields, the language is not always the same. So when we hear about supervised machine learning, there we're thinking about the model being supervised by the outcome. So we're trying to predict an outcome. We're trying to identify a diagnosis, for example, or to classify an image as problematic or not, or to predict whether a transaction is fraudulent or not. We've got an observation that has an outcome attached to it, and we're trying to predict that outcome. With unsupervised learning, we're trying to discover hidden features or patterns in the data. We don't have an outcome per se or a supervisor. We're trying to say, are there clusters in the data that might be evident? Are there, in the old-fashioned statistical world, principal components that might summarize the data neatly, or there might be other ways to summarize the data? We're just trying to say, how do these, let's say, images group together? And then I'm not going to talk much about reinforcement learning. Reinforcement learning is our models that learn from past experiences, where learning is updated based on achieving goals. So my understanding of this is that robots and things like that work with reinforcement learning. If things go well, it will keep doing what it's doing. If things go poorly, it'll change. So I want to just give a slight summary of the kinds of
Would you
algorithms.
save it as Innovation Solutions Canada or ISC or something that's unique?
On OneDrive?
Well, just send it back to me. Send it on.
I think someone is unmuted.
Send it.
There we go. So just a brief summary of the algorithms that we're working with, or some of the algorithms we can think about is, so machine learning algorithms, you'll sometimes see referring to tree-based methods. Classification and regression trees is an example, Bayesian regression trees, or random forests, which is running lots and lots of tree-based models and averaging across those. And tree-based models are exactly what you think they are. That is, you start with a big group of people or observations. With classification trees, you group them into homogeneous groups, and then you group those groups into homogeneous groups and so on, and you form what looks like a tree. And these methods can be very effective in classifying and supervised learning type problems. And then Bayesian trees and random forests are just extensions of that. There's lots and lots of methods that rely on penalization. So lasso being the most probably well-known example of penalization methods, basically says, if you have 100 covariates in your model, there's probably some chunk of those covariates where they don't matter that much to your model. And you can downweight those covariates and probably improve your model performance without creating too many problems. You can probably reduce the variance in your models without creating too much bias if you penalize these weakly associated covariates in the model. And then there are extensions of that, like elastic net is one, which I probably could not explain to you right now if I tried. And then there are methods that we've heard of in the news, like neural networks and deep learning, which use so-called layered methods, where the predictions are sort of layered on top of each other until there's a final prediction at the end. Then, of course, there are statistical methods for prediction, like linear regression, logistic regression, and Cox regression, which are sort of standard practice in epidemiology biostatistics. And I'm going to talk at the end, time permitting, about ensemble methods. And these are methods where, instead of saying, I'm going to run a cart-based tree or I'm going to run a lasso, we run several methods. And then we either pool or average the predictions, or we select the best prediction based on some criterion from this collection of methods. One example of ensemble methods that I've worked with that was developed by the group at Berkeley, Biostatistics and Epidemiology, is a so-called super learner, which is developed to do exactly as this bullet suggests, to take a bunch of methods and then average across them. And the idea behind this is sort of standard, statisticians would say central limit theorem theory. The average of a bunch of methods is bound to be better than any one of those methods by itself. There's also some simple language issues that we have to get past when we read machine learning literature. We talk about data points. Machine learners might talk about an instance. We talk about an outcome variable. They might talk about a label or an output. We might talk about a covariate or an independent variable. They might talk about a feature. We talk about a statistical method. They might talk about a machine learner. We talk about estimation. They talk about learning. These are just, this is a rough set of translations from the literature. So I'm going to dive into a couple of simple examples of how pharmacoepidemiologists can use machine learning tools. Okay, so I'm going to talk first a little bit about unsupervised learning. And unsupervised learning is quite potentially useful for what I'm hesitating, I guess computational biologists and others might refer to as phenotyping. Identifying features or clusters of features that come together to say, you know, this person has this condition, or this group of people are homogeneous with respect to this issue. And then that's also potentially useful for discovery, about thinking about are specific variables or latent clusters associated with use of medications or with specific outcomes. So this could lead to identifying subgroups, to new diagnostic criteria. It could be useful for prognosis or prediction research. And this is just a brief summary of the study indicated on their other side, just showing that some variables in the database are getting different weights. So being elderly, being female, being obese, having type 2 diabetes, being on sedatives is useful, are all variables that are useful for clustering out these populations. And then we see just five example clusters here. I don't want to go into too much detail here about the clusters, but I'll pick one here. Cluster number 5 is female over 60 with fracture history. This spider plot, the further you are from the center, the more important that variable is to the cluster. So these are just, this cluster identifies a homogeneous group with regard to risk that may be useful for future work. And this is all unsupervised learning. We didn't put an outcome into this. We just said, how do people cluster together? We don't know necessarily yet that this cluster is associated with bad outcomes or good outcomes. We just know that we've identified these 5 groups here. Okay, we can also look at supervised learning, that is now using an outcome to say, to work in signal detection. In this case, this is, can we use machine learning to predict associations between drugs and ADRs, that is adverse drug reactions, in this case, online databases. And this group of researchers basically went through this and showed that the gradient boosting classifier identified, and let's see, which is, I cannot remember which SSA stands for, but the gradient boosting method predicted 32 potential ADRs in this case, and the other method predicted 38. These among these known methods, only 2 methods, only 2 of the known associations were missed by both methods. On the other hand, 7 were missed by the SSA and not missed by the gradient boosting classifier. When we look at the unknown potential associations, we see a similar pattern. It looks like the gradient boosting is finding more potential associations than the standard method. And then, of course, that needs verification and is just a preliminary work, but it's just an indication that you can use these prediction methods to explore data and look for potential associations. So now I'm going to turn to stuff that I'm much more familiar with, and I think many of you will be more familiar with, just in terms of what can we do with machine learning for confounding control. And so now I'm putting myself in the setting of an epidemiologist or a biostatistician who has an observational study, and I want to find the effect of a treatment on an outcome, and I might want to use machine learning tools to control for confounding in that treatment outcome association. I'll start with a bit of a couple of punchline slides that summarize what I'm going to talk about, or the key points that I'm going to talk about in the next little while. This first one, I hope, is relatively clear already. Can machine learning alone control for confounding? And my answer is an emphatic no at this point. This first point is, I think, well known, that confounding control decisions require external information. You need to input information about whether, when variables occurred, whether they happened before the exposure or after the exposure, what you think the scientific structure of the problem is. You can't just use pure prediction methods to control for confounding. The strength of machine learning methods is that they work with the data only. They don't use external information to predict. They're supposed to be working just with the data, and they're good for prediction. And I think what I want to talk about today is, can they augment other methods that we work with? My second sort of punchline slide is one that we talk about all the time when we're studying epidemiology, but when we're reading the literature, we often see that this is not going so well in the literature. That, first of all, design trumps analysis. That is, if you have a badly designed study, you're not going to save it through statistical magic or machine learning magic. You're just stuck, and there's no way forward. So I'm going to make the assumption that we don't have that problem going forward. The second key message that I think is really important is that big data require the same statistical methods, statistical thought, and substantive thought about confounding in pharmacology as do small data. And in some ways, one can argue big data require more emphasis on statistical input and substantive input, because with large sample sizes, everything is going to be statistically significant or potentially statistically significant, and our confidence intervals are going to be really, really narrow. So we have to be a little more careful about what we're putting into those methods, because we know we're going to get results out. And there's no substitute for a good understanding of the source of the data generating process, and the science and the research question. So this I'm going to take as given, and I think if you look into the scientific press and the commercial pharma consulting world right now, you can come up with plenty of examples where this has failed. That is, people with access to lots of data and access to lots of computing power and machine learning power, but lacking understanding of the source of the data generating process, and the science, have produced some really flawed results. And there's just no substitute for the kind of stuff that we learn in our programs in epidemiology and biostatistics, and the kind of stuff that we consult our clinical colleagues for, and our clinical colleagues work with us on as well. But I want to talk today about how machine learning tools can help in some settings. So as I said, I'm kind of going to assume that I'm in good shape regarding design, study design. I have a well-designed cohort study, and I say here it may be helpful to think of this in the target trial framework. I have no immortal time bias, and I have a well-defined intervention, for example, treatment initiation. So I might think about initiation of high dose versus low dose statins as this well-defined cohort study, just to give myself something to frame this on. So everybody comes into an observational study at the same, at the same time zero. Some are given high dose statins, some are given low dose statins. There's no immortal time bias, and I've got lots of confounders measured. I'm going to assume this to be the case here too, because if I don't have lots of confounders measured, I can sort of pack up and go home or start doing sensitivity analyses. So this is a directed acyclic graph, or DAG, with treatment T, outcome Y, and covariates or confounding variables X. In the examples I'm going to be thinking of, X is going to be large. It may be in the hundreds to thousands of variables. And the key is I'm assuming X is sufficient to control for confounding. Or I spelled confounding wrong, I see in this slide here. So what do we do when we're faced with confounding and we want to do something with it? We want to control for confounding. Judea Pearl is one of the most well-known and well-written authors on this problem. And if you read his book, The Book of Why, or his more advanced book, Causality, he essentially says, if you know the directed acyclic graph, you're done. That is, if you expand out this graph to represent what you think reality is, then there's a set of rules that you can use to say, I should control for this set of variables in this way. And then once you've done that, you include all those relevant variables in your covariate set, and you're done. And I think it's a reasonable question to say, is that realistic? Because we don't know the DAG. We're making assumptions about what the DAG looks like and what covariates are in there. And so we may want to be a little bit cautious with this. Tyler Vanderweel, in a really nice short paper in European Journal of Epidemiology, said, it's simple, it's difficult to know the DAG. However, we could just say, let's include causes of exposure, let's include causes of outcome, let's exclude known instrumental variables. And there's a small discussion we could have about why this is interesting. But I'll leave that to see if time permits. And also to look for proxies of known confounders. So basically to say, let's just build a long list of potential confounders. Let's take out the ones we think might be harmful, and then we should be okay. That gets us to the point where we know what X is in this graph, or the set of variables that is X. The next step is, what do we do with X? And for the remainder of today, I'm going to focus on confounding control using things like the propensity score. And the propensity score is a really simple tool that is just a summary of the X variables. And it's a summary of the X variables that's written as, or derived as, the probability of T equals 1. So probability of being treated given X, the covariance. So in my example, I talked about high dose statins versus low dose statins. The propensity score, the simplest framing of the propensity score would be, it's the probability of being treated with high dose statins given covariance. And so everybody, we would fit this model, the propensity score model. Everybody would have a propensity score. Let's say mine is 0.3. So I have given that I'm in the data set, I have a 30% chance of being given a high dose statin, a 70% chance of being given a low dose statin. And what's nice about it is these are different ways of saying the same thing. In some mathematical sense, it's the best summary of the confounders. It's an efficient way of taking all of the confounding information that's in your data set and combining it into a single number. So what this is telling us, put another way, is all I need to know about me is that my propensity score is 0.3. So if I'm in the database and I have a propensity score of 0.3, and someone else is in the database and they also have a propensity score of 0.3, doesn't matter if we're different ages, different genders, different smoking habits, different exercise habits, different comorbidities, et cetera, as long as we both have the same propensity score. And that's a really nice feature because it allows us then to use the data efficiently, and we can use it by matching. For example, we could say, let's say I got a high dose statin. I'm going to be matched to someone who got a low dose statin who has the same propensity score. Or I could do inverse probability weighting and reweight people by using the propensity score so that we create two groups that after weighting look similar to each other. And I'm not going to spend too much time on actually using the propensity score because I want to focus on the propensity score itself as a tool for the last 20 minutes or so. I've talked a little bit about this first point here. On average, people with the same propensity score should be identical, and all we really care about is the propensity score. The key point on this slide, though, is this second point, that the propensity score is a prediction. I care that my propensity score is 0.3. I don't care about how my age affected my propensity score. Maybe I do for sensitivity analysis purposes or diagnostics. But in terms of the model itself, all I care about is my propensity score is 0.3. And so it seems logical right away to say, if all I care about is prediction, maybe I should be thinking about about different tools to fit the propensity score. Maybe I should be thinking about machine learning tools to fit the propensity score, because machine learning is about prediction. So, if I do logistic regression and get a propensity score of 0.3 versus elastic nets and get a propensity score of 0.3, those are both very different models. I don't care about interpretation of what's inside the model. I just care about the 0.3 at the end. So in pharmacoepidemiology, we often work with administrative claims data. And as I said, it may include hundreds of covariates or thousands of covariates. Some key confounders may be missing because it's administrative data. It's not research, not data created for research purposes. And the functional form of the propensity score may be difficult to determine. It may be difficult to fit the correct model. All of these points suggest machine learning might be a good idea here. So Sebastian Schneeweiss and colleagues developed what I've always referred to as a rudimentary machine learning tool, the high dimensional propensity score method to control for confounding, which basically just says, let's screen through those thousands of covariates. Let's look for covariates that are most likely to cause bias, most likely to be confounders. And this is an automated tool, so it's based on the numbers, not the substance. It's not saying, oh yeah, smoking is definitely a confounder, so I better include it. It's saying smoking has an odds ratio of this for treatment and this for outcome, so it's likely to be a confounder. It's data driven, and then it creates the propensity score based on a huge number of variables. And in response to Vanderweel and Pearl, Schneeweiss in this European Journal of Epidemiology paper wrote, all of that sort of structural theory about you could draw the DAG is all well and good, but when you have 1,000 covariates, you're not going to draw a DAG, and you're not going to go through them one by one, identifying which variables you think are associated with the outcome and which are associated with the exposure. You might as well use something like the high dimensional propensity score. Which leads now to I'm going to talk a little bit about some of our work, and I think I'll probably end up cutting the last part of our work a little bit short, but I'll talk a little bit about what we've done here. So the next natural step is to say, okay, the high dimensional propensity score is rudimentary machine learning. Maybe we should be using real machine learning to fit the propensity score. And so you could try things like the lasso. You could try things like trees that I mentioned earlier, random forests, bagging and boosting, which are other methods of ensembling different estimates together. Then there are others that I don't pretend to understand. If you go look on R, there are new algorithms being developed like this all the time. But you can also use this super learner.
I found this on the web.
Google search, my Siri just told me that Google search is updating their algorithms all the time. So we can do super learner, which is an ensemble average of a bunch of prediction algorithms, as I said. So Schneeweiss and colleagues compared HDPS matched methods to several others. They tried outcome models, they tried machine learning for the outcome, they tried machine learning for the propensity score, they tried Bayesian propensity scores. They tried as many as they could, a bunch of different methods that they could get their hands on. And their conclusion was it didn't make much difference. And I'll show you one of their results. And their results, they didn't do a simulation study, they just looked at a bunch of examples. And I don't need to go into detail on this slide other than to say this is a bunch of different methods with point estimates and confidence intervals around them. The one in the middle here is the high dimensional propensity score adjusted method. Aside from these ones over here, I think it's pretty clear that what they found is what they found, that the methods are essentially giving the same answer. So their approach was high dimensional propensity score is pretty much fine. Or their conclusion was high dimensional propensity score is pretty much fine. These machine learning methods don't add a ton of value. So a couple groups noted, but the HDPS pre-screens variables. And one of the things that it does to simplify the modeling is it converts variables to binary variables. So that makes it easy to fit a model because you're just fitting a bunch of X's that are zeros and ones. But it might lose information if there were continuous and nonlinear, continuous variables and potentially nonlinear associations included in the model. And so I'm going to skip over the next two slides here just briefly. This is just some motivating work by Romain Paracchio and colleagues. Ehsan Karim, who was a postdoc in my group, looked at this problem again, but saying, let's look at a survival outcome. Let's look at a bunch of potential machine learners. Let's look at a large number of covariates, and let's essentially see what happens. Can sort of standard logistic regression, high dimensional propensity score methods do as well as machine learning tools? And so he used these candidate learners, and I lose my understanding about halfway down this page here. I have, reasonable ideas of what random forests are, but I couldn't tell you exactly how these work. Importantly, though, he also looked at super learners, which would say, let's take all of these methods and take the average prediction and see whether that result works well. And I don't need to go into the details of these results other than the two big boxes over here. So if we know the functional form of the propensity score model, so if we're in the Judea-Pearl DAG world, we know which X's are important and we know how they predict treatment, then whatever method we use works pretty well. And in fact, ordinary logistic regression or Bayesian logistic regression give very small bias and very small mean squared error in a simulation study. Superlearner actually gives slightly better mean square error at the penalty of a little bit of bias. On the other hand, if we don't know the method, that is, if our logistic model is specified incorrectly, this is where machine learning really helps us. If we don't know what's going on and we have the machine learning methods sort of constrained in a controlled space where all they're doing is building this prediction model, so that all they're doing is building a prediction for the treatment, the propensity score, then, excuse me, the superlearner method, the averaging of a bunch of machine learning tools, does far better than anything else, both in terms of bias and mean square error. So the idea there is, if we don't know what the propensity score looks like, but we have a reasonably good idea that our covariate set is good, then superlearner machine learning tools can be quite effective at fitting the propensity score and then producing good outcome results. I think I will just very briefly mention this second set of slides. Sorry, the last time I realized as I was preparing these slides that the last time I gave this talk, I had closer to an hour and 20 minutes to do it. So I'm probably going to need to squeeze things here and there. This is just to say, Asa and Karim also looked at what we'll call a hybrid approach, where maybe the high dimensional propensity score method, which does this variable screening at the beginning, is useful, but in collaboration with machine learning tools. So let's say if we have 10,000 covariates, we might not want to fit a machine learning tool with all 10,000 because we might be here for weeks just waiting for the propensity score model to fit. Maybe we can use the HDPS algorithm to say these are the most likely to be candidate predictors, and then run machine learning algorithms on it. And I'll skip over the work here, other than to say, if you're not familiar with plasmode simulations, this is an extremely useful tool that we could have another easily spend an hour just talking about these. The idea here is, rather than simulating data by just generating covariates from thin air, you start with a real study and then you manipulate something in the study and then you sample from that data set and you manipulate something and you sample and so on and so on. So your simulations are much more realistic than they are when you do it sort of the old-fashioned way. Plasmode, we used a plasmode simulation looking at statin use post-myocardial infarction. I see a question in the chat that's anticipating some follow-up here. And the long and short of this was the results were somewhat mixed, but the hybrid methods using high dimensional propensity score to screen and then machine learning to fit the models did reasonably well in terms of predicting, in terms of getting the outcomes. Now, Pamela is asking the question about using superlearner in the propensity score model and this issue of single robustness. And so, as I said, you've anticipated what's about to come next, which is there are at least theoretical problems with the way what I've just presented works. That is, you can end up in a situation where you're asymptotically, that is in very large samples, introducing bias by fitting machine learning on the propensity score by itself. But what you can do then is do something that we refer to as double robust methods. And here I'm going to have to go very briefly, just because of time, I think I'm coming close to the end and I want to leave a few minutes for questions, but I'll give just the highlights of this. And so what we typically do, or what was typically done in epidemiology for the last 50 years, was we regress the outcome on our treatment and our covariates, and our coefficient for T measures the effect of T on Y. This is a model for the outcome. And that, we can do a logistic regression model, we get an odds ratio, everything is fine. Machine learning may misfire here because the focus of machine learning is on predicting Y. It's not on that coefficient for T, and that's a problem. Propensity scores, we can regress T on X and then match or weight on the propensity score and then estimate the coefficient for T using that matched sample or that weighted sample. And that works as we were just discussing. There's potential problems there, at least theoretically, with machine learning tools for the propensity score. On the other hand, in both cases, we're dependent on either this model being correct or this model being correct in order to make our method, our approach work. And double robust methods were developed to say, well, why don't we do both models and use them in a intelligent way to combine information about the results. So if we fit a model for the outcome, that is, how do the covariates predict the outcome? If we fit a model for the treatment, that is our propensity score, and we combine them in an appropriate way, we can do better than using either model by itself. And under the right circumstances, this is this property of double robustness. That is, if either model 1 or model 2 is correctly specified, then we can get an unbiased estimate of the treatment effects. And that's great, because now we've got sort of two chances to get the model right. And the key then to the machine learning key is that model 1 and model 2 can be prediction models. We don't need to interpret those coefficients. Again, we can use machine learning tools appropriately here. So I think I won't go into this next step of double robust methods and targeted learning or targeted maximum likelihood. All this to say, this is a very simple heuristic of what we do here. We build an outcome model. We try to predict the outcome. We can use a high dimensional machine learning method. We build a model for the treatment. That's the propensity score. And again, we can use a high dimensional machine learning method if we want to. And then we combine the two models in an appropriate way. And I'll skip over these next slides I'll give the reference to anybody who wants to. This was a study, just rerunning a study of statins on statins post-MI and looking at mortality and looking at targeted maximum likelihood, the double robust methods under a variety of settings, and showing that they did reasonably well, in particular compared to inverse probability weighted models, which is what sort of we standard would have used in the past. So in conclusion, machine learning has lots of potential uses in pharmacoepidemiology. It can be used really well for exploratory analyses if we're wanting just to discover potential associations. It can be used in pharmacovigilance for the same things. It can be used in causal inference, as I outlined, if we want to compare two treatments. And I didn't go into any detail on this last example of looking at the effect of statins post-MI. It can be used to get better estimates of those treatment effects. It needs external information. And the whole idea behind what I've been describing is machine learning tools are great for prediction. We can use them, like in the targeted maximum likelihood setting, for prediction. We can't use them for causal inference by themselves. And I've sort of tucked this in, but the high dimensional propensity score and other methods like this can be used as well. When we've got lots of binary covariates and we've got simple administrative data, they are fairly interesting. And then these hybrid methods are interesting as well. So I'll stop there and I'll just note Ehsan Karim, Menglan Pang, Tibor Schuster, a number of other students, a number of other colleagues who did a lot of this work, and funding from CIHR, FRQS, and NSERC, and CNODES, which drove the initiative for a lot of this work over the last 10 or 12 years. And I'll stop there. And I think I left only a few minutes for questions, but I'll take any if there are any.
Thank you very much, Robert. I'm just going to turn over to the audience. Any questions for Robert? Let me ask one then in the meantime. So Robert, you mentioned a DAG there briefly, usage of a DAG, but then you caution that it's useful only so long as you're able to specify the correct DAG and the the correct relationships involved. So, I mean, and I find this is actually very confusing because I've been trying to make DAGs during the last year, and I'm still not convinced that they're more useful than probabilistic equations, which I guess I learned and maybe I'm still more familiar with.
So I think I'm going to flip back and I'll draw that again. I think I'll just I guess I share your reservations a little bit, and my reservations come from sort of similar spaces. One is, if you have a pretty good understanding of what's going on, I'm not sure the DAG adds a ton of value. And the other thing is, when you get to a problem that is remotely realistic, your DAG is just incredibly complex. And the odds of it being incorrectly specified once it's incredibly complex are probably quite high. And so I'm just not sure. I'm not sure it adds value in a lot of problems. Where DAGs clearly add value for me is in conceptual understanding of ideas, like understanding confounding as, you have a covariate that is affects the outcome and it affects the treatment, and or drawing DAGs for selection bias, I think those are really helpful. But I'm not sure that I think this idea that you're putting down a set of assumptions and then doing the analysis as if they're right, the risk of misspecifying things and the risk of creating problems for yourself if you misspecify things is high enough that I'm somewhat skeptical about the usefulness. So yeah, I think you and I share some concerns there.
Any other questions for Robert? I mean, I feel like the gist of your talk
Hey,
is
Robert.
that, yes, Jay.
Yeah. Hey, Robert. Thanks for the talk. Do you ever see a day where machine learning is actually going to be useful for causal inference? And, I mean, I think it's a given that it can be useful for prediction. It can certainly go into models that the human mind is not even capable of conceiving. But the more interesting question for me is whether machine learning can ever be used for causal inference to predict interventions, the effect of interventions. Do you think we'll see that day?
My gut feeling from that is that I think we need there would need to be a quantum leap in machine learning to get there in some sense. That is, with the tools we have now, I'd say no, and perhaps with future tools, I'm still skeptical, just because I think we run into limitations of. I think we may also run into limitations on data, and not just data size, but data, the sort of signal to noise ratios in data, and I've given examples like this, I use the credit card example because that's billions and billions of transactions where the data set is being generated it is being refreshed every second, and the variable, the outcome is relatively constrained, fraudulent or not. It's not like we're talking about a cancer diagnosis where you might be talking about subtypes of some specific kind of cancer. You might talk about misdiagnosis and so on and so forth. It's a much more constrained problem. This is the other one that I think of that's a much more constrained problem is the traffic prediction. So I don't know if others use Waze in their car. Waze is doing machine learning along the way to predict the best route for you, but it's dealing with enormous amounts of data relative to what we're dealing with and much simpler problems. That is, if I come out of my house and I'm driving west on Sherbrooke and I need to know which is the fastest way to the airport, there are going to be people who have gone to the airport or past the airport 15 minutes before me, 20 minutes before me, 30 minutes before me. There's lots and lots of data about that case. Whereas again, if we're dealing with clinical outcomes, the amount of covariates we're dealing with, the sample size we're dealing with, the signals in that are just not as complex. So I'm somewhat skeptical that we'll ever do much more than what we're talking about here, that it'll be used as tools within algorithms, but not by itself. I'm just answering Pamela's question in the chat, and the short answer is yes. The question is, it's preferable to use superlearner or machine learning tools with targeted maximum likelihood or other double robust methods rather than for the propensity score by itself. And my short answer is yes. My longer answer is yes, but I think it remains to be seen how bad those biases are in practice. but that's probably an opportunity for some research as well.
Okay, thank you very much, Robert. Jay, did we answer your question? Do you have any other comments?
No, just to thank Robert for the talk. It's a very good overview of where we're at, and obviously much work remains to be done.
Excellent. Yes, no, I agree. It's a good area for sure.
Thank you very much, Robert.
Excellent. Thank you.
Have a nice evening, everyone.